Hello again, thanks for watching this video and studying math with me. This is the fourth and final video in this series of Chapter 5, and so I probably don't even have to say this again about pencil and paper in hand. The last embellishment on this model that we're going to do is by introducing a forcing function. And in the model you might think about this, saying I'm going to take this platform and somebody is moving this platform up and down and back and forth, and that could be an example of our forcing function that's happening while the spring is acting as well. So we're adding this forcing function or non-zero right hand side. Now how this affects our model then is we have this f of t function, lowercase f of t, that is now on this side, which is driving things, and the response is the other side. So if we move these two terms to the original side because they involve the function x and its derivative, then we have this by itself here, and we divide all the way through by m, we get this expression. And now lowercase f over m becomes the uppercase f of t, and as in the preceding sections, the 2 lambda is the beta over m, and the omega squared is as before. And so that's the model. Now all the students will recognize that now we're talking about a non-homogeneous equation that we have to solve. So we're going to be solving both the particular solution, and we're going to also have complementary solutions. Let's look at an example, and here is the example we're going to use. Now this is different than the ones we've talked about before, maybe for the first time. We have a 3 kilogram object. We've started using the metric system. A 3 kilogram object, that is mass already, is attached to a spring, and it stretches the spring 392 millimeters. We have to think about the powers of 10 here by itself. There is no damping in the system, and the forcing function is of this form. Capital F of t is equal to 10. This is cosine omega t, and that's attached to the object. So what we have is a forcing function. And we say the system will experience resonance. Now resonance means that the forcing function, this one here, has the same frequency as the fundamental system frequency. And we'll talk about that. But this number here, we're going to use this same thing as what we had as omega in the on the other side that's associated with the system. And you might remember that omega is the square root of k over m. And so we're going to have the same frequency, and we'll see what happens. We also have some different initial conditions. The object is initially displaced 20 centimeters now downward. You have to pay attention to the powers of 10 from its equilibrium position, and given a velocity of 10 centimeters per second upward. We want to find the displacement at any time t, and we're going to call that u of t. Okay, so here we go. Now, as before, we have to find the spring constant. This is a different spring. And so what we have is mg. So there is the 3 kilograms. But now the acceleration due to gravity in the MKS system, I'm taking to be 9.8. I'm dividing that by 0.392 because I'm changing that to meters. And I will get 75 as the spring constant. Now, since the system is experiencing resonance, we know that the frequency here was the square root of k over m, and that's going to be k was 75 over 3. That's going to be 25. The square root of 25 is 5, so that's the natural frequency. So now, since there is no damping, we have the mass times the acceleration, so it's 3 u double prime plus, and this is going to be omega squared, actually this is going to be, let's see, yeah, this is going to be 3 that, and we're going to have this 75 here as that number. We're going to divide by the 3 in a minute, and this is going to be 10 cosine 5t. So you see we're matching up this frequency with that frequency, and here are our initial conditions changed into meters. Okay. Now, when we solve this equation, what we're going to have is d squared plus 25. That means we're going to get in our complementary solution cosine 5t and sine 5t, That's going to be a linear combination of those. That's my complementary solution. But then we have to, either by annihilators or variation of parameters or Laplace transforms or something, we have to figure out what we have on this side, and what we have when we solve it is it's going to be 1/3 t times sine of 5t. I can use my initial conditions to come up with what these coefficients actually are. So it's 1/5 cosine 5t minus 1/50 sine 5t plus, this is going to be 1/3 t times sine of 5t. Now I am going to change this into, at least I'm going to change this first part of this into the amplitude form, and so I do that with these coefficients, and I look to see what phi is. By the way, for the first time I get one of these phis that is actually in the fourth quadrant, and so that has a negative number. So this is a negative times a negative, because this was cosine of 5t minus that phi, and so minus and minus ends up being a plus, and this is the amplitude that I have. So u of t is equal to 0.20998 times the cosine of this plus 1/3 t sine of 5t. But think about this. This one is bouncing up and down like a nicely behaved cosine thing, but this one is going to start oscillating wildly, because although sine stays between 0 and 1, t keeps growing bigger and bigger. So here is the graph that we get. So the oscillation starts like this, but it starts growing, and as t gets bigger, the oscillation gets wilder and wilder and wilder. Eventually, this is going to break your spring, or it's going to break whatever system you have, perhaps the airplane wings that you've designed and things like that. So you see, resonance is something to be avoided at all cost, because that will result in the utter destruction of your system. I don't care how strong you build the system, this kind of behavior will tear it apart over time. Now, although pure resonance is unlikely to occur because some form of damping is usually present, large and very destructive oscillations can occur, so engineers need to be very sensitive to this idea. Let's look at one final example, and in this one we're going to take the system from the last example, but now we are going to put in a damper, and the damper that we're putting in will exert a force of 45 newtons when the velocity is 50 centimeters per second. Okay, so we will look at this. Notice that we're paying attention to the fact that it's 50 centimeters and that was newtons. You have to worry about the units and powers of 10 just a little bit, but you're going to get that beta is equal to 90. And so the initial value problem then is similar to the one we had before, except this coefficient then is going to be 90 instead of it being 0 as it was in the pure resonance case. And we get 75 there, and we're staying with the cosine of 5t there. And so we get these initial conditions. But this time, when we solve this, it comes out different, because we have two roots and two real roots. So this is minus 15 plus 10 root 2, and this is minus 15 minus 10 root 2. That is my complementary solution. And my particular solution this time becomes 1/45 sine of 5t. So when I plug this into a calculator and look at the graph of this, I find that I have this exponential function and this exponential function that are associated with the initial conditions, but you see they're e to the minus powers, so these are dropping off over time, but I continue to have this amplitude, small amplitude of a sine function working off into time. So the picture of this will look more or less like this, and so you see that I have some things happening at the beginning that are called transient elements of solution, because they kind of die out as t gets bigger, but then we go into what is called a steady state mode, and that's the steady state solutions. And so we can see both of those things here in this problem. Now, just to close with an analogy, and there are many analogies to this modeling approach and also to these equations. If we have an electrical system where this is an inductance coil, that's a resistor, that's a capacitor, and we do have a driving force, which is like a battery or a power source that's coming in, this is the equation that we get. Now here L stands for the inductance, Q is the charge, and we have this kind of differential equation. And we see that this differential equation looks exactly like this differential equation. All you have to do is replace L and M. R is the resistance, which was what we talked about before, and you have the reciprocal of the capacitance that is that, and you see it really is exactly the same set of differential equations that you're going to solve. So that completes a discussion, as much a discussion as we have time for in Chapter 5. As we go forward, as always, time is precious. Each day must count. Do the math. It will make you strong. Take care, and I'll see you in class.